Welcome back to the deep dive. Today, we are strapping in for a fascinating look at infrastructure, specifically the unseen economic engine powering this explosion of AI voice technology.
It's a big one.
It really is. We're not just looking at a better algorithm today, we're examining a fundamental re-engineering of the entire cost structure behind text-to-speech, or TTS.
That's right. We are embarking on a truly deep dive into the concept behind a startup called ParrotSpeech. And their goal is, well, it's incredibly ambitious.
That's putting it lightly.
They want to be the Stripe of voice. Now, think about Stripe for a second. They made integrating payments so simple, so cheap, that it became the default choice for practically every startup.
It just became part of the background plumbing of the internet.
Exactly. ParrotSpeech wants to do the exact same thing for high-quality, real-time voice generation. The idea is to drive the cost down so low that it becomes a near-free utility layer.
Yeah.
Like basic internet connectivity or IP packets.
Okay, let's unpack this, because the core conflict here is what makes this so compelling. We're dealing with a stack of sources that highlight this massive financial friction that's currently jamming up modern voice AI. And the profound question ParrotSpeech is trying to answer is this: why are we still paying premium, sometimes prohibitive prices like, 30 per $1 million characters for TTS from modern providers like 11 Labs?
Right.
When at the same time, these ubiquitous services like Google Translate or Discord or Telegram can give you high-throughput, real-time voice processing for essentially nothing.
And that's the disconnect.
Yeah.
The difference, as our sources analyze in depth, is a physical, hardware-based one. It's a structural dependency on specialized hardware.
Okay.
Those expensive, high-quality systems, the ones that produce the most natural-sounding voices, they rely heavily on massive parallel matrix computations.
Which means GPUs.
Which means they are inextricably linked to specialized and very, very expensive GPUs. ParrotSpeech is proposing a radical architectural overhaul designed to break that dependency completely.
And if they do that,
They can instantly drop their operating costs down to the level of, say, an efficiently run high-performance web server.
So our mission today is to really analyze this: the technical roadmap, the algorithms, and the strategic decisions that supposedly make this near-free cost structure not just possible, but sustainable.
And if this concept is validated, the implications are just enormous.
For everything. Every application that uses voice, from customer service bots and accessibility tools to, virtual worlds and gaming NPCs.
We're talking about commoditizing the entire voice layer of the internet.
Let's start by defining the problem that ParrotSpeech is attacking. Why is advanced high-quality TTS currently so prohibitive for widespread mass-scale integration? It really comes down to the astronomical cost of the underlying AI infrastructure.
It's not just high cost. It is, and this is the key, a fundamentally unsustainable cost structure for any service aiming for high volume and low margin. Let's just look at the hardware required for modern AI inference. We're talking about specialized GPUs like the NVIDIA A100s or the newer, even more expensive H100s.
The ones everyone is scrambling to get their hands on.
Exactly. And these aren't just expensive, their prices are volatile and constantly increasing due to scarcity and demand. That makes it incredibly difficult for any company, especially a new startup-to-scale, modern, high-quality TTS systems economically.
So just to open the door and even compete on quality, the initial capital expenditure is massive. You need a whole farm of these specialized chips just to handle the volume, creating this huge upfront barrier.
Precisely. That initial infrastructure investment required just to purchase the hardware for a competitive GPU farm, which you absolutely need if you're running state-of-the-art diffusion or large autoregressive models, is staggering.
And the result of that?
The inevitable result of having such high-priced specialized hardware is that the return on investment, the ROI for that infrastructure, just drops through the floor.
I see.
Startups, who are often operating on a limited runway and seeking rapid growth, they face these massive capital expenditure risks when they tie their core product scalability to such expensive and volatile hardware.
And they have no choice but to pass that cost directly on to the consumer.
Which is why we see that $30 million character's price tag.
This sounds less like a temporary market issue and more like a deep structural problem that fundamentally prevents anyone from ever achieving that true utility level of cheapness, like cloud storage or basic email.
That is the core tension they are exploiting. Our sources emphasize this massive cost gap between running AI inference on specialized GPUs versus general-purpose CPUs.
And what sort of gap are we talking about?
This differential is frequently cited as being 5 to 10 times higher for GPU operations compared to optimized CPU operations.
5 to 10 times.
Yes. So if the hardware is 5 to 10 times more expensive to run for every single request, you can never sustainably achieve a mass market, near-free price point. That cost gap is the fundamental barrier that ParrotSpeech must and plans to close.
And the proof that mass scale, low-cost scaling is actually possible already exists, right? It's in plain sight.
Absolutely. We have the low-cost benchmark provided by services like Discord, Telegram, and Google Translate. They handle astronomical numbers of requests, they achieve extremely high throughput, and they maintain ultra-low operational costs. Precisely because their core processing routines run highly efficiently on standard commodity CPU servers. They don't need a dedicated air-cooled H100 GPU cluster just to translate a sentence or process a few megabytes of data.
So that demonstrates the potential.
It demonstrates the immense financial potential, the mass-scale near-free cost model that becomes immediately accessible the very moment you successfully engineer the GPU requirement out of the system.
But the conventional wisdom for years now has been that modern, natural-sounding TTS requires that massive parallel processing that only a GPU can provide. So if the hardware cost is the issue, then the solution has to be a radical re-engineering of how the compute happens, not just moving it somewhere else.
It demands nothing less than a total architectural overhaul, combined with some bleeding-edge algorithmic optimization.
And the pressure is on.
The time pressure is immense because the market is just exploding.
Yeah.
We're talking about a global TTS market that is projected to hit well over $5 billion within the next 5 to 7 years. It has a robust compound annual growth rate.
Then what's fueling that?
It's all these new applications. Conversational voice AI, agents like ChatGPT voice, customer service bots, specialized virtual assistants. This growth highlights an urgent, unfilled need for a highly cost-effective, easily integrated TTS solution.
So everyone needs voice, but the GPU tax is crippling innovation at the scale of, say, millions of small developers.
That's a great way to put it, the GPU tax.
The sources mention using standard high-performance CPU servers, specifically AMD EPYC servers. Now, for a non-expert, this sounds a bit like trying to use a truck to win a Formula One race. Can a standard server CPU, even a really good one, actually handle the computational complexity of generating human-quality speech?
That's where the engineering genius comes in. And you're right, AMD EPYC servers are inherently weaker than a specialized GPU in terms of raw parallel processing power. They are built for different tasks.
Right.
However, they're fantastic at sequential tasks and high I/O throughput. So ParrotSpeech's strategy is not to make the CPU as fast as a GPU, but to make the workload light enough and sequential enough for the CPU to handle it at massive scale.
How do they possibly accomplish that without just wrecking the quality?
The key is extreme optimization, specifically leveraging the deep internal caching structures within the CPU, the L1, L2, and L3 caches.
Okay, break that down for us.
Think of a large research library. The main server farm, the GPU cluster, has all the books, but it takes time to get them. The CPU has a complex system of local shelves. The L1 cache is the tiny shelf right on your desk, which is lightning-fast access. L2 is the nearby rolling cart, and L3 is the room right next to your office.
So the goal is to only keep the absolute most critical, most frequently needed data for the TTS process right there on those nearest shelves.
Exactly. By carefully architecting their processes, specifically the encoder and the MEL spectrogram generation, to leverage this internal caching, they keep the working data set small and frequently accessible within the CPU's fastest memory structures.
And that lets the CPU.
It allows the CPU to achieve extremely high throughput for those lighter initial processing stages. It starts to mimic the efficiency of a high-volume web server rather than requiring a dedicated compute cluster for every single request.
So the goal isn't achieving absolute maximum speed, but achieving sufficient speed at a near-zero marginal cost. That's what allows them to undercut the entire market. That's the structural breakthrough.
Precisely. They are betting that optimized, cheap speed beats specialized, expensive speed for the vast majority of the market.
Okay, so let's unpack this structural breakthrough. This distributed architecture is really the economic lifeblood of the whole near-free model. ParrotSpeech is fundamentally rejecting the monolithic server-side pipeline by splitting the computational burden between their server and the listener's own client device.
This architectural split is the core mechanism that achieves their cost savings. And to really appreciate the innovation here, let's just briefly revisit the standard 5-stage TTS pipeline.
Okay.
It starts with text, which is broken down into a character or phone representation. This then feeds into an encoder, which learns the patterns and generates a compressed acoustic representation called the Mel spectrogram.
And the last two stages are where the actual sound gets made.
Right. The final two stages are the most critical for generating sound. The vocoder takes that Mel spectrogram and reconstructs the raw waveform, which is the actual sound file you hear.
And as we established, all the competitors run all 5 of those stages, including that final heavy vocoder on the cloud, likely on an expensive GPU, and then they charge you for it.
Right. ParrotSpeech radically segments this responsibility. The server retains only the parts that can be heavily optimized and are suitable for mass, low-cost CPU processing.
So just detail that again for us. What stays on the server side, running exclusively on those cost-effective AMD EPYC servers we just talked about?
The server handles the initial language modeling intensive stages. That's the conversion from the initial text or phone data through the encoder and culminating in the Mel spectrogram generation.
And that middle part is what's been fine-tuned for the CPU.
Exactly. It needs to be fast, accurate, and high quality, but crucially, it's the part that can be algorithmically fine-tuned for efficient CPU architecture using those cache optimizations we mentioned. They specifically target robust commodity hardware, citing instances like the Hessner dedicated instances, which offer a high CPU core count and high-speed memory for excellent throughput per dollar.
So the server sends a highly compressed preprocessed signal, the Mel spectrogram, which is tiny compared to a raw audio file, and then the server's job is just done.
That is the structural stroke of genius. The final, most computationally demanding and bandwidth-heavy part, the vocoder stage, is pushed entirely to the client device.
I see.
This means the task of converting that compact Mel spectrogram into the final large raw waveform is no longer ParrotSpeech's financial burden. It's the user's device's responsibility.
The benefit of that shift has to be dramatic, right? I mean, reduced server load, minimal bandwidth use, and operating costs that barely even register because the heavy lifting is offloaded.
It fundamentally alters the unit economics.
Uh,
The server load is massively reduced, the bandwidth requirements plummet because they're only streaming a tiny Mel spectrogram instead of a full audio stream.
right.
And the operating cost model scales naturally and essentially for free as their user base grows. They don't need to constantly purchase and provision more expensive server-side GPUs.
Now, here's the catch. This is the skepticism required in a deep dive. Running a complex vocoder, even an optimized version of something like Big VJan or Hi-Fi Jan, reliably on a consumer client side, a browser, a phone, a tablet, that sounds like you're asking for massive headaches, lag, and battery drain.
It does.
So how do they address execution across this dizzying array of devices?
That's where they rely on cutting-edge browser technology. The execution is handled using WebGPU. Now, for our listeners who haven't tracked browser tech closely, WebGPU is the successor to WebGL. It's a modern API designed specifically to allow high-performance compute tasks and graphics processing to run right inside the browser environment, leveraging native hardware acceleration.
So WebGPU allows the vocoder to use the processing power that's already available on the user's device, the integrated GPU, or even the specialized NPU, the neural processing unit, found in newer mobile devices.
Precisely. It maximizes resource utilization. It uses the user's local GPU or NPU for lightning-fast inference. And if those specialized units aren't available, say, on an older laptop or a basic browser, it just falls back gracefully, though a bit slower, to the CPU.
But the key is the server never has to see that final heavy compute.
Never. That's how ParrotSpeech maintains its low cost.
But the models themselves, the vocoder weights, they must still be relatively large. You can't ask a user to download a gigabyte of data every time they open a chat window. That would completely destroy the user experience.
That's a great point. And that is solved by their intelligent caching strategy. The full vocoder weights are not treated as a single massive file. They are split into small binary chunks, designed to be around 10 to 20 megabytes each.
Manageable chunks.
Right. And these manageable chunks are then persistently stored in the browser's IndexedDB.
And IndexedDB is the key here, right? It's not just the temporary browser cache that gets wiped.
Exactly. IndexedDB is designed for persistent, client-side storage of large amounts of structured data. This means the weights are only downloaded once, during the initial access or setup.
And after that,
All subsequent uses rely entirely on that local cache. This hugely reduces bandwidth requirements, it eliminates repetitive downloads, and it ensures that subsequent inference speeds are nearly instantaneous, limited only by how fast the server can stream that tiny Mel spectrogram.
and beyond the cost and performance benefits, this architectural choice also seems to address one of the biggest current concerns in AI infrastructure: Privacy.
Yes, and this is a major competitive differentiator, especially for enterprise clients. Since the vocoder runs locally, the conversion from the mil spectrogram to the final raw waveform happens entirely within the user's browser or application.
Meaning the final audible audio file never needs to be transmitted back to ParrotSpeech's servers.
Or stored in their cloud. Never.
Which makes the system inherently compliant for use cases in a highly regulated environment.
Absolutely. I mean, think about healthcare records, financial transcripts, or internal corporate communications that are subject to strict regulations like GDPR or high payer.
Data sovereignty is paramount.
It is. And by ensuring the final synthesized voice, which could contain sensitive spoken information, never leaves the client, ParrotSpeech builds a formidable competitive moat rooted in privacy and compliance. That's something their GPU-focused competitors often really struggle with.
This distributed architecture is incredibly clever from an economic and privacy standpoint, but it's still, a house of cards if the server-side, CPU-only MEL spectrogram generation isn't just blindingly fast.
No.
If that CPU is sluggish, the latency targets fall apart, and we're just back to a painful, laggy voice bot. So what is the algorithmic secret sauce that makes the CPU fast enough to hold up its half of the bargain?
Okay, so we shift now from architecture to pure mathematics. The speed and quality gain comes from adopting and heavily optimizing new generative modeling techniques that are inherently more efficient than older standards.
So not diffusion models.
Right. Instead of relying on traditional, slow, iterative diffusion models, the core MEL spectrogram generation uses flow matching, which is similar to techniques popularized in models like FITTS as its baseline.
I understand flow matching is already a step up in speed over diffusion, but what enhancements did ParrotSpeech add to ensure stability, quality, and that extreme efficiency specifically for a CPU?
They apply two critical related concepts, diffeomorphic fields and the central optimization, which is stationary velocity fields, or SVF.
Okay, let's start with diffeomorphic field.
Right. Think of this as an engineering guarantee. This concept ensures a smooth, invertible, that's the diffeomorphic part mapping, during the conversion process between the starting point, a simple noise distribution, and the complex target distribution, the MEL spectrogram.
Why is a smooth invertible mapping so critical for quality speech? Can you give us an analogy?
Sure. Think of it like drawing. If you're drawing a complex object, a smooth invertible mapping means you can trace the final outline all the way back to the original simple sketch without any sudden jumps or broken lines.
I see.
In the context of sound, this stability leads to high-quality MEL spectrograms with significantly reduced noise and fewer audible artifacts like buzzing or clicking. It essentially guarantees that the complex pattern the vocoder receives is clean and robust.
Oh, it's a quality assurance layer, basically.
Exactly. It results in a far more natural, artifact-free final voice.
That locks in the quality. But for pure, unadulterated speed on the CPU, we need these stationary velocity fields, which sounds like something from advanced fluid dynamics.
It is advanced physics-inspired optimization applied to machine learning. SVF is the main CPU speed-up lever. In traditional generative models, the ones that are just too slow for CPUs, you often require dozens of iterative steps, sometimes 20, 50, or even more, to slowly refine the noise into the final, coherent MEL spectrogram.
And each one of those steps is a separate compute cycle.
Right, which limits the speed severely.
So what does the stationary velocity field concept fundamentally change about that process?
It drastically reduces the complexity and the number of steps required, because the underlying velocity field, the direction the model must move in, is stationary, meaning non-changing across the integration time. The model can take these massive jumps.
How massive? What kind of reduction are we talking about?
The sources cite a reduction from the typical 20 to 50 steps all the way down to a mere 5 to 10 steps.
Wait, hold on. So they took something that normally requires 50 calculation steps, and this one algorithmic modification, SVF, cuts it down to 5 or 10. That sounds a bit like marketing hype. How solid is that engineering claim, and what does it translate to in real-world speed?
That is the crucial point that needs validation, and it is the engineering core of the entire startup. The claimed performance impact translates directly into a 3 to 5 times speed increase for the MEL spectrogram generation process itself.
Wow.
So if we accept the claim by requiring far fewer calculations, this optimization drastically lowers the overall compute requirement, making real-time, high-speed MEL spectrogram generation entirely viable on a commodity CPU server. It is an algorithmic solution that essentially solves the hardware constraint if the math holds up.
Now let's talk about the final product's naturalness. That's essential for any modern voice agent. When you use real-time streaming, the voice often sounds robotic or flat, because the system doesn't know the proper intonation or emphasis until the very end of the sentence. How does ParrotSpeech tackle this problem in a streaming environment?
They address this with an advanced feature they call phase-aware prosody modeling. Standard TTS models traditionally only predict the magnitude, the volume, or power of the MEL spectrogram. ParrotSpeech integrates the prediction of phase information in addition to the magnitude.
Phase information, that is extremely technical. Can you give us a simplified analogy for how that helps with the flow and coherence?
Yeah, think of it this way. A traditional system waits until you finish the sentence to see the period or the question mark before it decides what your overall tone should have been. It then has to rush to adjust the pitch contour, and that often sounds unnatural.
Right.
ParrotSpeech, by incorporating phase information combined with prosody signals like pitch and energy, is like having a musician listening to the timing, the rhythm, and the harmony of the sentence as it's being built.
So it can actually predict the pitch and energy cues before the sentence is even finished.
Exactly.
Huh.
In a streaming or conversational scenario, the system can enable these crucial real-time adjustments. If the model detects prosody cues mid-sentence that indicate a question is forming, that natural rising tension in the pitch, it can start raising the pitch contour immediately.
Which would vastly improve the naturalness.
It eliminates those telltale robot voice artifacts, especially in dialogue. And this level of responsiveness is vital for targeting their key performance metric. The ultra-low latency mode, where the TTFB, or time to first byte, must be below 150 milliseconds.
Let's pause on that 150 millisecond TTFB target. For our listeners, why does that specific number matter so much in a conversational context?
Because human conversation just breaks down when delays exceed that threshold. Anything over 150 milliseconds is generally perceptible as a lag or a pause and makes the AI feel slow or interruptible. When you interact with a conversational agent, if you have to wait 500 milliseconds for the first syllable to even start streaming, the flow is completely broken. By aiming for sub-150 milliseconds, they are targeting true, near-instantaneous, human-like conversational responsiveness.
And that's the ultimate upsell for any B2B agent platform.
That's the holy grail.
So ParrotSpeech has a fundamentally cheaper engine built on the back of the CPU client split and the SVF optimization. Now, let's move from analyzing the engine to seeing how they plan to weaponize that low cost against the market giants. Their strategy is crystal clear. Integration first, prioritizing penetration over immediate feature parity.
That strategic intent is really the only logical move when you possess such a structural cost advantage. They recognize they cannot beat the entrenched giants on every single feature, at least not yet.
Right.
But they can utterly crush them on the unit economics. The goal is to make using ParrotSpeech so economically sensible that integration becomes the default, low-friction choice for any developer or platform.
Tell us about the initial minimum viable product, the MVP scope, for the first 6 months. It sounds extremely focused, almost counterintuitively narrow.
It is focused with surgical precision. The MVP has a strict mandate. Prove the unit economics and the quality in a very limited context. The sources state a strict initial focus on one single language, even if 70 languages are the long-term goal, and only 1 or 2 standard voices, male and female, per language initially.
Why limit themselves so severely? I mean, isn't the market demanding more languages, more voices?
It is, but this limitation is strategic risk management. It allows them to allocate all of their engineering resources to achieving flawless quality and hitting that critical low-latency target within that narrow scope.
So they can prove it works perfectly in one area first.
Right. For example, if they choose a high-growth, underserved market like Vietnamese or a major European language like French, they can achieve excellence and validate their cost model rapidly, rather than spreading their compute power thin across dozens of just average-sounding voices.
And the entire purpose of this tight focus is validation of the near-free thesis.
Absolutely. The primary objective is achieving near-zero marginal cost per inference to ensure that for millions of developers and platforms, using ParrotSpeech becomes a no-brainer, a utility purchase rather than a capital cost decision.
And this strategic advantage, it unlocks 3 massive benefits that rapidly build their defensibility.
It does. Let's walk through them.
Okay, what's the first one?
First, massive integration. By offering a cost that is, 10 to 30 times lower than the competition, They instantly become the accessible go-to choice for every indie developer, every small chatbot builder, and any massive platform that needs to scale volume without incurring prohibitive operational costs.
They basically bypass the entire procurement headache that comes with expensive cloud service contracts.
Exactly. That massive integration then generates immediate trust and brand recognition, right?
Which leads to the second advantage.
Reputation and reach. This is the core of their go-to-market strategy, Phase 1. By offering high quality at an unprecedented, disruptive price point, they rapidly build credibility within the developer community. This viral adoption is key. Developers share tools that save them money, leveraging word-of-mouth and open-source principles to achieve rapid, low-cost customer acquisition.
And finally, the crucial self-improving advantage for any AI company, the data feedback loop.
Yes, the third advantage is data collection. Gaining a large user base through this low-cost entry allows them to continuously collect usage data, always with transparent consent, of course, across diverse real-world use cases.
And that creates a virtuous cycle.
A powerful one. This high-volume, real-world data collection creates a virtuous feedback loop, where massive adoption leads to richer data, which leads to continuously improved models, better prosody, better naturalness, which in turn fuels further integration and adoption.
Let's put this into competitive context using the specific numbers provided in the sources, because this is where the market disruption becomes undeniable.
The cost difference is stark. We need to look at the industry standard metric, cost per million characters.
Okay.
Market leaders who rely on the full GPU stack have high baseline costs. 11 Labs sits around $30 per million characters for standard usage. Google Cloud TTS, even leveraging their economies of scale, ranges from $4 to $16 per million, depending on the voice model and volume commitments.
And ParrotSpeech, what's their target?
ParrotSpeech, specifically targeting large enterprise volume pricing, aims for a range of big or 50 to $1 billion characters.
50 cents to $1. Let's contextualize that for the listener.
Okay, if $30 buys you, say, 10 minutes of synthesized high-quality dialogue, 50 cents to $1 buys you the entire script of a feature-length novel or a massive video game repeated dozens of times over.
That is a cost dominance that ranges from 30x against the high end of the market to a crushing 4x to 16x against a cloud giant like Google.
It's an almost insurmountable advantage.
That structural cost advantage is impossible for incumbents to match. They would literally have to dismantle their profitable GPU infrastructure just to compete.
It creates a situation where competitors relying on the full GPU stack simply cannot enter a price war without committing financial suicide. They would collapse their existing business model and invalidate billions of dollars of infrastructure investment.
And on top of that, ParrotSpeech's scalability is inherently superior.
Because of the offload architecture. It moves the bottleneck, the expensive limited pool of server-side GPUs, to the client, where the compute capacity is virtually infinite and, crucially, free to ParrotSpeech.
This cost structure allows them to be the basic, reliable infrastructure layer that everyone just plugs into, the definition of the Stripe of voice.
It's the classic infrastructure play. Commoditize the underlying resource, in this case voice generation, to capture the layer above it, the data, the features, the marketplaces.
Now we have to address the most challenging question for any company aiming to be near free. If you're offering the core service at almost no cost, how do you actually monetize it? And critically, what stops a deep-pocketed giant like Google or OpenAI from simply replicating the architecture and crushing them?
They monetize latency and exclusivity. They leverage the low base cost to acquire users and build market share. Then they upsell on features that truly require enterprise commitment, speed, and customization.
Okay, so walk us through the pricing tiers, starting with that vital free tier that's designed for rapid adoption.
The free tier is designed to be extremely generous, 100,000 characters per month with standard latency. And crucially, it requires attribution that powered by ParrotSpeech badge.
So it's a viral marketing tool.
It's a viral marketing tool and a foundational low-cost data collection funnel. It allows thousands of small developers to validate their ideas using the platform at absolutely no cost.
So they gain integration, free advertising, and crucial real-world usage data in exchange for the service. What about the tiers that actually generate profit?
The paid tiers monetize volume, premium voices, and most importantly, performance. The starter tier at $19 a month and the pro tier at $99 a month, they unlock high volume, up to 10 million characters, and critical premium features.
Especially that ultra-low latency mode.
That's the one. That ultra-low latency mode, the sub-150 millisecond TTFB, is clearly the massive upsell for any serious enterprise or conversational AI company.
And the Pro tier is what gets you that.
Absolutely. The Pro tier targets that necessary time to first byte of under 150 meters, utilizing a high-speed streaming API or WebSocket. This is indispensable for high-stakes conversational agents, where any perceptible delay just breaks the immersion. These tiers also unlock unlimited voice selection, advanced voice cloning capabilities, and dedicated training for enterprise clients.
And the enterprise tier handles the largest clients, likely those who need the ultimate in privacy and scale.
Correct. The enterprise solution provides custom volume pricing, which is where that 0.850 to 1 per $1 million character target is realized dedicated support, guaranteed SLAs for uptime, and the option for on-premise deployment.
And that on-premise option is a huge competitive edge.
Huge, especially against general-purpose cloud providers who insist on hosting the entire stack.
Let's discuss the go-to-market strategy, which seems to rely heavily on that initial viral push into the developer community.
The strategy is phased and integrated. Phase 1 is the developer community, the viral entry. They plan to open source the client code and vocoder weights, providing transparency and allowing community contributions.
So they'll be on Product Hunt, Hacker News, all of that.
Launching aggressively on platforms like that builds immediate trust and buzz. They'll target partnerships with indie game developers, accessibility tools, and small chatbot builders who are currently just priced out of the high-quality PTS market.
And once that community is established, they move up to B2B platforms.
That's phase 2, B2B integration. This targets commercial platforms, customer service systems, e-learning platforms, and digital content creation tools. And a critical focus here is deep integration with workflow tools like Zapier and Make.com.
Why is that so important?
If ParrotSpeech becomes a standard action item in popular automation platforms, their reach multiplies exponentially without needing a massive, costly, direct sales team for every single client.
And the final long-term phase involves building a robust network effect that locks in their market position.
That is phase 3, the voice marketplace. This is a masterstroke in building a sustainable, scalable moat. They plan to allow professional voice actors and creators to sell licensed copies of their unique voices on the platform.
So ParrotSpeech becomes the broker.
They manage the licensing, the hosting, the underlying cloning technology, taking a modest 30% cut while the creator receives 70% of the revenue. This builds a powerful network effect. A diverse, high-quality voice library attracts more users, which attracts more professional creators, cementing ParrotSpeech as the essential hub for custom voice licensing and training.
That brings us back to the competitive moat. You mentioned a larger company could replicate the architecture. What are the specific pillars that protect ParrotSpeech from being easily crushed?
They rely on intertwining technological and economic defenses. There are really 4 pillars.
Okay, start with the technology itself, the engineering IP.
Pillar 1, technology. The proprietary or published research surrounding diffeomorphic flow, matching with stationary velocity fields, SVF, is a unique technical differentiator. This is their engineering head start. If they can achieve early patent protection or, more realistically, establish this highly optimized, CPU-first approach as the de facto standard for integration by open sourcing the client stack, they create a technological barrier to entry.
Then comes the economics, which you said is the strongest pillar because it's impossible for competitors to match without self-cannibalization.
Pillar 2, unit economics. This is the strongest structural moat. Their architecture is fundamentally designed to eliminate the server-side GPU cost. They possess pricing power that their competitors simply cannot sustainably match.
Right.
Trying to enter a race to the bottom against ParrotSpeech would force competitors relying on full GPU infrastructure to run at a massive loss, potentially killing their core, profitable business lines. The structural low cost is their financial armor.
The third pillar is the classic AI defense, data and network effect.
Pillar 3, data and network effect. The high initial adoption, fueled by the near-free entry point, generates a proprietary stream of unique usage data. This data continuously improves their model, making it more natural and responsive.
And the voice marketplace reinforces that.
It does. The growing collection of unique, high-quality licensed voices becomes an exclusive asset, attracting more users and tightening the network effect, making the platform more valuable the more it is used.
And finally, the integration focus.
Pillar 4, infrastructure lock-in. They are not selling a feature. They are creating an indispensable infrastructure layer. If thousands of companies build their customer service bots, e-learning platforms, and accessibility tools on the ParrotSpeech API because of its rock-bottom cost and high reliability, switching becomes prohibitively expensive and time-consuming. Infrastructure creates network effects that are incredibly hard to dislodge.
Looking ahead, the roadmap shows how ParrotSpeech plans to evolve quickly from that focused MVP into a full-service competitive platform.
Right. The immediate expansion phase, spanning 6 to 12 months, focuses on achieving scale and core feature parity across more markets.
So what are the key deliverables we can expect in that crucial 6-12-month window?
The priority is scaling languages quickly but strategically. After validating the core model, they plan to introduce 3 to 5 key Asian languages, citing significant growth markets like Vietnamese, Thai, Indonesian, Japanese, and Korean.
And new features.
They will also introduce core services like voice cloning, optimized to require only a short input, just 30 to 60 seconds of audio. And perhaps most critically for developers, they will launch comprehensive SDKs across all major platforms, JavaScript, Python, and React Native, to make integration effortless.
They also have a list of more advanced differentiating features designed to fully leverage their unique architectural split.
Yes. The first feature is a direct mitigation of their biggest technical risk, the hybrid inference strategy.
Which means
Recognizing that web GPU adoption is not universal, they won't force users onto the client. Users will be able to choose between full client inference, which maximizes privacy and offloads all compute, or a server vocoder fallback.
for low-end devices or browsers without web GPU.
Exactly. This ensures service continuity regardless of the user's hardware.
And what about specializing the voice quality for specific industry applications? You wouldn't want the same cadence and tone for reading the news as you would for a medical diagnosis.
That's where the vertical models come in. They plan to create domain-specific models trained on targeted data sets. For example, models specifically optimized for healthcare terminology to ensure accurate pronunciation of complex medical terms. Educational voices designed for standard, clear pronunciation, or specialized models tailored for news reading with the appropriate pacing and intonation for long-form content.
And that moves them up the value chain.
Towards bespoke enterprise solutions, absolutely.
For their B2B enterprise clients, operational insights must be crucial for optimizing usage and costs.
Yes, so they plan to offer a sophisticated voice analytics dashboard. This is more than just a usage counter. It will give B2B customers deep insights into usage patterns, error rates, and the performance metrics of different voices, allowing them to optimize their costs and improve the user experience based on concrete data.
So they can A/B test different voice personalities, for example.
Exactly. Track completion rates for agent dialogues, see which intonation patterns work best, all of that.
We've established the opportunity and the strategy, but no ambitious startup tackling fundamental infrastructure is without major risk. What are the highest impact risks they face, particularly around technology and competition?
The sources outline 3 critical areas: technical adoption, performance targets, and existential competition.
Let's start with the technical adoption challenge.
The highest impact technical risk is the pace of web GPU adoption. If browser support and user hardware adoption of web GPU lags significantly, their core efficiency model, the client-side offload, is jeopardized.
But, as we discussed, this is mitigated by offering that server-side vocoder fallback.
Right. The system doesn't fail, it just becomes slightly more expensive to operate for those specific users. The second key risk is hitting those aggressive latency targets. Achieving that sub-150 millisecond TTFB is an enormous engineering challenge, mitigated only by relentless optimization of the flow matching steps and aggressive caching strategies.
The business risks seem even more existential, particularly the threat of large corporations just commoditizing the service.
That is the ultimate threat, and it's rated as very high impact. The possibility of Google, OpenAI, or Amazon offering free or nearly free TTS as a standard developer service is very real.
And if a major player decides to commoditize the service overnight?
ParrotSpeech's core pricing advantage is undermined. We've seen this happen historically. Think about cloud storage becoming virtually free, or high-definition video conferencing becoming a standard free feature in platforms like Zoom or Microsoft Teams.
If that happens, how do they mitigate that threat? Their competitive moat relies so heavily on price.
Mitigation requires multi-pronged excellence beyond just price. First, rapid execution. They must validate their unit economics and lock in those infrastructure contracts quickly.
Okay.
Second, they have to leverage their niche focuses. Focusing heavily on the privacy-first architecture with guaranteed on-premise deployment gives them an immediate segment in highly regulated industries, finance, government, healthcare, where Google or OpenAI's generic cloud offering may not pass compliance.
And finally, the marketplace.
Leveraging the voice marketplace to acquire exclusive, licensed voice assets creates differentiation that cannot be easily replicated by a generic model.
And finally, we have to address the ethical and legal risks associated with voice technology, particularly as they move into cloning.
This is a non-negotiable area. To manage the risks associated with deepfakes and misuse, they must implement strict legal and technical safeguards. This includes requiring explicit consent audio for verification before activating any cloning service.
And watermarking.
They have to implement watermarking technology within the generated audio to allow for tracking and detection of synthesized output. And furthermore, the creation of the voice marketplace demands a clear, robust legal framework for copyright, licensing, and royalty distribution to protect the voice actors contributing to the platform. Transparency regarding deepfake concerns is mandatory.
That technical complexity, the tight margins, and the looming presence of these enormous competitors requires almost flawless execution. It seems like the entire success hinges on proving those unit economics early. Can they truly deliver high quality for under $1 per million characters consistently?
That is the core challenge. They have to measure and audit relentlessly. The successful pairing of the SVF optimization with the web GPU offload is the foundation. If they can validate that incredibly low cost per inference early on a small cohort and demonstrate that the performance holds up across diverse client hardware, then the entire business model becomes validated, and that stripe of voice vision becomes not just a dream, but a highly likely outcome.
What an incredible deep dive into the engineering and economic architecture of voice AI. ParrotSpeech isn't just trying to build a better TTS model, they're fundamentally trying to democratize the entire technology by moving the compute boundary away from centralized, expensive hardware.
By shifting the heaviest lifting, the vocoder, from the expensive, capital-intensive cloud infrastructure to the ubiquitous, decentralized client device, they have engineered a structural way to eliminate the high cost of specialized AI hardware.
They're turning a major capital expenditure problem into a manageable operating expense problem.
That's it.
And the core strength is that pairing of high-level engineering and shrewd economic strategy, combining innovative flow matching optimized for CPU efficiency using stationary velocity fields with a radically distributed architecture. That results in a product that can undercut the price of the entire existing market.
It creates a new level of accessibility that transcends mere feature development. They are selling a dream where voice technology is no longer constrained by the financial friction of GPU costs, making high-quality, real-time voice accessible to every developer, every small application builder, and every corner of the digital ecosystem.
Which leaves us with a truly provocative thought, one that we have to consider as the cost of this technology plummets. If high-quality, real-time text-to-speech becomes a near-zero marginal cost infrastructure layer, what happens to the human voice in the digital domain?
If every chatbot, every game and PC, every customer service interaction can sound perfectly natural, emotionally nuanced, and instantly generated, will the perceived value and uniqueness of synthesized speech drop entirely to zero? Will it just become an expected, invisible utility?
And if this structural cost advantage accelerates the ability to create perfect synthesized voices in real time, will it accelerate the deepfake challenge, making it impossible to distinguish between a real human voice and synthesized speech in live conversation?
Or will synthesized speech simply become an invisible utility like electricity, or those IP packets we started talking about, seamlessly integrated into the fabric of the digital world without causing any friction at all?
That's something to mull over as the age of the near-free voice truly begins.
A fascinating, if slightly daunting, thought to end on.
Until the next deep dive, keep questioning the infrastructure beneath the surface. We'll see you soon.